All right, sound test. Can you hear me? Hello. Okay, that's amazing. That's very good. I will have to prepare a VVVV yet, so that will come a bit later. Until then, you will see this loop, and at 4 o'clock, hopefully, we will start out. I can't. Let me hear myself a little bit. Is the background noise too much, or should I do anything with that? Okay, I will close the windows because I'm not doing laundry, but my studio. Okay, unfortunately, my microphone stands on the table, so I can't really do anything with the keyboard. Sorry about that. Currently, I'm using for microphone a Kinect 1 because it is the best what I could find. The alternative would be a webcam microphone. So the background noise is that we are located. I'm in the studio. I'm in the vvorkshops studio, and we are located in a curve, in a very, very steep curve. With the curved rails going on from Liverpool Street. All the trains are going to northeast London. They will go through this curve here, and it's horrible. I will shut the windows. It will be much better. Is it better? All right, then sound is good for me then. If it is good for you, I will do some VVVV still. Everybody sees the stream in HD. I can see it in HD. It's all right. I will start about an hour or something. Yeah, well, you have an hour. Buy chips and cokes and stuff. Don't worry. I'm planning to start at 4, but maybe I will start like 10 or 20 minutes later than that. Nice one. Yes, it is. That's actually a VVVV patch. And it is not real time though. It is and it's hello there. So yeah, that is quite some hacking around with the link. Yes, I'm cutting off the microphone because I'm coughing sometimes, so I don't really want to traumatize you with that. It's not that terrible though, but you know, just like that. I don't really want to get that into the stream or something. Okay, then if everything is fine, you will just see this loop for an hour, probably. Because I started this test so early because this is my first time, first on YouTube, first on streaming on anything. So I wanted to make sure everything works, and if something would have gone terribly wrong, I would still have time to do that. So anyone can do something else until 4 o'clock. It is starting at 4 p.m. London time. This is where I am. So it is 5 p.m. for rest of Europe. Oh yeah, anybody here from Germany? I've seen your egg from. Are you from Germany? Yes, yes, exactly. Yeah, yeah, I will just write. Okay, is the proxy good? Or I still have to switch over to Twitch? Should I? Well, for the next episode. I don't know about proxies. Can't post links here. Oh yeah. Oh, I don't know. I don't know that. Try replacing the punctuations with spaces, so we can just write that in. Do you have a paid account on ZenMate? Your egg seems to be one which is just meaningful when you get it with a paid account. Okay. So you say you should stick with Google? No, it's okay. Just if it's free. All right. I cannot touch this. And the reason I chose Google over Twitch, first of all, Twitch is kinda game centric, and I don't know how it fits in there. And second, I already had a Google account, and I didn't want it to have another service into the pipeline. I will post this zenmade.com on Facebook, so people can watch this from Germany then, apparently then. Hello there. Hello folks, as you could guess, it's Michael D here. So yeah, I think we can start out. So let me switch from this video, which is going on for ages now, to something more meaningful. So currently, as you can see, hello there, I'm streaming from vvorkshops. This is where I work, and yeah, let's get started, shall we? Oh yes, indeed. First of all, you can see a link. I will post it again if I can find the text. You can see a link to vveekend. Creative director. Wow. No, I'm not. I'm far away from a creative director. Ooh, you have stuttery sound. Let me listen to that just a second. Yep, sound is busted. Okay, I'm out to fix that. First. Yep. I'm working on that. Okay, just a second. I will put back the looping video. Okay, let us see if it is what I've done fixed the thing or not. Ah. Yeah, much better. Okay then. I will put this out because this is disturbing to hear myself in the future or in the past. This time travel. So starting again. This room here, what you can see is vvorkshops. I will put that over there. So this is vvorkshops. This is where I'm streaming from London, and if everybody's all right, we can start out. So again, there is a link to a prepared vvv which I recommend you to download from. I will send it again. So I recommend you to download this vvv because this has all the packs which I'm using as well during this workshop, and also some other goodies which you might be interested. So And also, disclaimer, this is the first kind of event. This is my first actual online streaming. So prepare for some improvisational nature of the war show, and probably in the edited version, this war thing will be cut out. Other jazz is that what you can see. All right, let's start out. I've opened here a www patch, which you will be able to follow in a second. I will upload these as well, and I will switch to my desktop also in a second. I will zip these and switch to desktop. That and that. Oh, this is spoiler alert. Where can I share this? Share. Advanced. Change. Anyone with the link? Okay. Here are some patches what we will work on today. Oh man. I will post this into IRC as well. As you can see, there are very few of them. A reason for that, I didn't have much time to prepare them. But we will do some other jazz on the fly. Anyway, if I switch to my desktop, you can see here. Yes, I've switched to the desktop right now. Just there is some delay, so be prepared for that. I might react a little bit slowly to comments. It looks like, but in nature it is just a delay of the stream, I guess. So anyway. Here we can see, first of all, one thing I have to point out. Look at this camera. Everyone open this patch. It's OO gimbal lock. We will look into that, yes. Look into the dispatch and look at this camera. First of all, delete space mouse if you don't have space mouse or VJoy, because that might mess up things. And so this camera is way better than what we have in add-on packs. The reason is that, first of all, the cursor will stay where you actually direct it, so it won't go out of the renderer at any time. Also, you can have multiple devices connected up to the same camera and connected up to the same way. Oh, hello there! That's the only thing I don't like in this hardware. Okay. So I recommend using this. If you, oh yes, other feature is with that you can set up your keyboards, and you can set up your ways of controlling the camera as well. Even it has the WSAD controls for you to play around, so you need to move around your camera more, like in a game. You can set up all sorts of jazz with the keys. And you can also emulate the old school soft image camera, what you have in our DOM pack. Do we have that in native vvvv? Yeah, I think we have that in native vvvv. Anyway, also disclaimer, look at this axis and grid. This is a different one which comes with the DirectX 11. This looks a little bit nicer and there's a little bit waste, I mean more, there's more space in it, and presumably faster, but I don't think so. Now the topic of the workshop. So you can have 3 types of rotations in vvvv, well, actually 4, because transformation can be rotation as well, but that's yeah. What's your error in the patch? So if anybody has error opening that patch, can please tell me. Or send a screenshot. That's even better, send a screenshot. Because I might have left something out. Oh, okay. Well, you can live without axis and grid. That's not important to the wall plot. It just helps navigating around. But actually, where this is, yeah. Or if you double click it and choose one of these. This is the default DirectX 11 axis and grid. I don't know why it is messed up for me. And this is the one coming from MCRO pack. So if you double click it, if it's not there, then you can delete it. It's not important. So if anyone is alright, I would start out. Everyone is okay, great, works, nice, okay. So where did I left? Yeah, there are 3 explicit types of rotation in vvvv which are actually used for rotation. Is the Euler, which I presume everybody is very, very familiar with. Axis and grid and Quaternion. Actually, axis and grid and Quaternion are very close to each other, so they will be kind of dealt with at the same time. And now the Euler is very, very comfortable. As you can see, it's just like pitch, yo, rolls. It's like nothing what you haven't seen already. However, there are a couple of problems with the Euler rotation. We're actually using just a single rotate node. Is that you have to keep, when you do your rotations, you have to keep in mind the order of your rotations, and I will explain that. So the order means that these transforms, what you see on the pins of these rotate, does not happen at the same time. they are happening one after the other, and in a very, very strange format. So it's not really happening in pitch yaw roll order, but it happens in your pitch roll order. And I will demonstrate that. You can see these circles. These kind of represent a virtual gimbal device. So we can see the actual rotation hierarchy, what is going on. And you can see the monkey as well from Blender. Oh my god, what I've clicked. Oh, sorry. That was a mistake. So with these things, as you can see, let's go in order first then. As you can see, if I rotate around the y-axis, so that's the yaw, my other rotations will change their axis. The base axis of those rotations will no longer be the global axis, what you would expect, I guess. I don't know what you would expect though. And so when I pitch, notice that the axis of the rotation is no longer this red line here. It's no longer the global x-axis. And again, the same applies to yaw. About to say applies to roll. Sorry. That the actual axis of the rotation is very much distorted by the previous rotations, like as yaw and pitch. And there's the very famous problem with that, is the gimbal lock. With gimbal lock, if I rotate to 90 degrees, one of it's the pitch to 90 degrees, you can immediately see a problem there, is that one of our axes lined up. That's a problem, because now if I rotate on the first rotation, so that's yaw, so that will rotate around the global x-axis, obviously. My pitch, look at my pitch, made the z-axis of the roll align up to the y, of the global y-axis. So basically, if I do yaw, roll will be the same. And everybody is, I guess, not everybody, but the majority of vvv users who started out at some point and used vvv a couple of times have gone into this problem that they wanted to achieve a certain angle of a 3D object, and they found themselves locked inside this situation. I found myself locked in these situations a lot of times, actually. So yeah, that's a problem with that. Also, I can demonstrate this on other. Actually, there's another thing. I can demonstrate this with the other way around. So when I rotate the roll at 90 degrees, actually, the pitch. So I can line up these things very badly. So why is that a problem? There's another patch showing that in animation. Oh yeah, first of all, because before I go to animation, I will release a very easy solution for this problem. Is what you can already see here. Just use different rotate nodes after one another. So it's like super easy to solve that. However, you have to keep your rotation order in mind, and keeping that in mind, actually in arbitrary situations where you don't really know what will I don't really know the constraints of your object. Like, for example, this camera is working like that. It doesn't really know the constraints of its object. It will know the constraints of the next and the previous frame, but it doesn't know the constraints of the whole word. So if you don't know those constraints, and then you will end up with a pretty much headache. I will show you what that means in animation. I will start this, the gimbal lock animation problem. Actually, I should have used Control W instead of quitting the wall patch. And as you can see, I want to fade from our gimbal lock situation to another rotation. So I want to fade from here to to here. And as you can see already, there were some problems with that. It's not really making a straight line. I mean, not a straight line, but a nice curve. It kind of has this bend. So that's the main problem you want to avoid the gimbal lock most of the time. And also, some side note: the line is a new kind of line. It is not the one which is provided in DirectX 11. There, I have to still work on that. So this is kind of like a teaser for that as well. So you can see it throws this little arc, what we don't really want. And to avoid that, so that was kind of the 5 minutes of rotation, of Euler rotation. Well, I left it in there. That was the 5 minutes of Euler rotation, I guess. We can use quaternions to make this problem go away. The advantages of quaternions is that you can make any kind from any rotation to another rotation, or any position to another position. You can go without any kind of axis constraint, with the same amount of path. I will show you that in a second. So yeah, that was a quick one on this patch. So as you can see, he's actually saying, "Oh man, I forgot to use Control W." So here we are I will talk a little bit about the math of Quaternion. Actually, I won't really talk much about the math of Quaternion because it is super hard. I mean, I'm not really good with theoretical mathematics, and well, obviously that will be hard for me. But it's like complex numbers on steroids, and we will go for that in a second. Therefore, for this part of the workshop, we just have to accept that this is a collection of 4 numbers which represents a point on a 3 sphere, or represents a point in a 4D sphere, somehow that can rotate things in 3D. I don't entirely know that. I couldn't entirely grasp that from the Wikipedia page. Anyway, how to construct these quaternions. Oh yeah, actually, I have a better idea. I won't do this patch now yet. I will go back to this patch. And rotate the same thing, but with quaternion. So I will fade the animation. We don't need the line now. So we fade the animation with fading between quaternions. And one way of construct quaternions is to use the Euler. So that will convert a traditional Euler rotation, what you are used to from the rotate node in the matrix. This will construct as a quaternion. Actually, I will duplicate this. 125 0. And here as well. And here are the things. Long beards. It is. It is one. It is some unkempt long beard. I have to do something with that. And I'll be using a node called slurp. So this one, slurp, stands for spherical interpolation. Hence, it is going from one point on the 3 sphere to another point of the 3 sphere. So that's why it is, I guess this is why it's called spherical interpolation. And you could go the shorter arc or longer arc, but most of the time you are good with shorter arc. I will show the difference between them. So let's connect this one here, and we have our sphere here. Yes, and our line. Very nice. And now look what happens. Whoa, something. Oh, okay. Sorry about that. Little mishap. So now look, we have now the shortest way of rotating compared to the previous. I will call up the previous. Let's save this as Kimballock release. Solution. Okay, and I will bring up the other one for comparison. Oh geez, okay. Oh, accidentally saved it. Oh my god. Look, that is awkward. That is very awkward. So back to the topic. So as you can see, this one was our interpolation using only the Euler kind of rotation, the traditional rotation, and actually we don't need these toruses. We need that here. Don't need it here. So as you can see, we have a direct rotation between the two Euler instead of using the other way around. Yeah. So that, and that's why in such situations, if you don't know your constraints, it is way much more easy. As you could see, it is very easy to set up a situation like that. Oh yeah, the difference between short and long arcs. So this is long arc. As you can see, it goes the other way around. On the not yeah, on the longest possible way to go around the sphere. So here's a shorter arc. So what you could do with these is actually already demonstrated inside vvvv using inside the module called rotate and successive vector, and this is you can define an angular speed, and it will rotate an object like a motor with that angular speed. And inside that module, as you can see, they are converting the Euler angular speed into quaternions again. And all sorts of jazz is happening here as well. We will have a look at that later. So for example, like multiplying together two quaternions. Oh my god. So that's another thing what we can do with quaternions. But we can't really do with Eulers is that we can sort of add rotations. Not add, but multiply rotations with each other in a similar kind of fashion how we multiply matrices. So let me demonstrate that. Let's use this patch. So for example, if I want to reproduce the same artifacts what we had with the gimbal long, it would be much like, instead of lerping, now we will I will, before doing any damage, I will save this, and I will save it into different location. Say, and let's call it quaternion multiplication. So instead of lerping between two rotations here, now we will try to reproduce the gimbal lock situation what we had in the previous patch. So let's do that, and we have this. What is it? So multiply quaternion, obviously, And note, as with transformation matrices, I will go into that. I just realized that that will be part of this workshop later. So yeah, you can multiply together transformation matrices, these ones which are coming out, and these ones actually matrices if anybody didn't know that. So that much like them, it is not commutative. So it will give you a different rotation. This one won't give you different rotation because this is equal, this is not rotating at all, but it will give you different rotation with a different order of multiplication. So let me show you that. We have this quaternion here, and let's have this up here. As you can see, I can move around, and we actually don't have the same problem. Oh, look at that. All right, we don't have the same problem. Oh, we have the same problem. As you can see, even here, I pitched up 90 degrees, and even here, if I just roll this around, it will roll around the global z-axis, even with the Euler, because these kind of rotations have a quite strange order. If I do the inverse, you see how the order moves around. So it is now actually, as you could see before, in this situation, the pitch roll, it is a little bit backwards here. So if we want to draw similarity between the two systems, and we can see that the what is on top here, and which will be in the end of the matrices, it will be the first rotation in case of quaternions. So in simpler terms, it will be flipped, the order of rotations. The order how you have to connect them will be flipped. So as you can see now, we reproduce the Grimbar lock with the quaternion multiply signs. So you can multiply these rotations together, which is amazing. Because as I said before, in the rotate successive node, so it's like that. Yeah. In this one, they're using this this behavior to well, I'm searching for the word when I'm stopping. So they're using this behavior to use incremental rotation around any kind of axis without any kind of constraint. I will demonstrate that shortly, returning to the animation problem. So we have this nice fella here again, and now we've done with fading rotations. We want this monkey to rotate on an axis. So we will do that. So for example, if we want that monkey to rotate around the pitch axis, for example, that's all right. We will just have an integrate, have a speed, and as you can see, and as you could expect, it will rotate around nicely. Ta-da! Okay. So it will rotate around nicely. Okay, we can do this with all different axes. So nothing unexpected here. Actually, we don't see the line because the line is not rotated at all. I mean, it is aligned on this axis, the point, what the line was following on. Anyway, okay, let us see, let us presume, or let us make that we want to rotate this monkey in a similar fashion what we've seen here. So we want to rotate monkey continuously like this, but not on the x-axis. We want to rotate it on I don't know, on this axis over here. It's like the monkey head will rotate in this fashion, as you could see. So all right, how should we do that with Eulers? Let us see. Let's connect this. Okay, this is okay, as you can see that we have a problem because this is not rotating in a straight line at all. I mean, look, it is cool, it draws cool shapes, but even if I connect up, okay, this is going completely berserk. So alright, well, you see, in Euler you can obviously align up your rotation and then do something like this, and so you have it there. Just line follows. So you have it there, but cool guys don't do that. So what happens here can be expressed via only a single node. Actually, it can be expressed only via a single node. Using we'll switch to the other one and visit it back. Using a node called axis angle, you could see that coming, didn't you? So with this node, and actually Quaternion is kind of the same. You will see some similarities going on. So I can set up an axis like this, and to show this axis, I will throw an arrow that normalizing. Throw this arrow. Okay, and I will multiply it, just it will be visible. Alright, so we have our axis here. Alright, so we have our axis here. Let's be a little bit. Monkey's getting dizzy. Oh. Yeah, poor monkey. So as you could see, it would be pretty hard to do the same pointing this axis and then do this. So we'll pointing this axis and then do this. So what will do this to us is that now I exchanged the. And look, if we rotate around the axis without any kind of hesitation, I can turn the line back on. Actually, I will just expose this. Okay. Yeah, that's kind of nature of groups and dynamic pin nodes were complained a lot about in VVV forums. You have to open the inspector and all that jazz. So see if we can have this. Okay, all sorts of jazz is happening with the line. Anyway, if we go the same, we connect this integrate into our angle, we will have a nice rotation around the axis. As you could see, what we only could achieve with rotate nodes here. We will be able to, it's like rotating this around, but yeah, that's sort of like trial and error style of programming, which I also do sometimes. I'm not really qualified to judge, but it is a lot more safer to do. And so this one here, and to reproduce this. So what happens if we say that, okay, all right, we don't we would use this thing in a system where we don't actually know how the rotation is constructed. So over here we can do this kind of smooth rotation. This is a circular, very nice rotation here, because and we can do this continuously, because we are doing the continuous nature of this system inside constructing our quaternion, and then just don't care about the quaternion value, just pass it over to rotate, and the rotate node will calculate the transformation matrix out of that. We will talk about that later. So the transformation matrix out of that. Actually, we won't go into the math of how that's done. That's because Wikipedia is there for you if you're that interested. And the other thing is that you don't really need to know unless you want to replicate the same things inside shader. Then again, Wikipedia is there for you, or Google with Quaternion to matrix C++, and then you will have the shader example. Anyway, that is way much more advanced using this whole thing in shader. What this workshop at this point is should be. So let's get back to what I distracted from. Is that, let's assume we want to create a system where we can define the amount of rotation with a quaternion constructed by Euler, and with another quaternion constructed by axis angle. Okay, we will save that. Actually, we. Okay, no. That's. I was not supposed to say that. Save that. As. I'm completely out of control now, so we will just save that, and let's hope that you people will remember what was the origins of this patch. So anyway, let's have our axis angle. Yeah, let's reset that, turn off the line for now, because that will just produce us some gibberish. We want one of this, and we want this. And that. Now we want these to be the speed of the rotation, the velocity of the rotation, and that's a very nice thing to do there. We will use again requested. Oh no, not that multiply. Quaternion multiply. What is this? So this will be your speed of rotation. We can even, you know what? We can even slurp. Let's do that instead of multiplying them. So we can control that nicely. And then what we will do frame delay. And because I will just first I will show you a simple rotation. So the frame delay. Whoop! You have your treats over there. So okay, let's chill this fella down. So, I prefer this monkey to C++ Quaternion. Yeah, I've just brought up the C++ version because usually the C++ code, what you can see works, or even better, the C code works pretty much out of the box in HLSL. But yeah, you'd still prefer the Dizzy Monkey to HLSL Quaternions. I prefer the Dizzy Monkey than that as well. So as you can see, our problem with that, with any kind of incremental system, is that our speeds depend. Oh, I already had a main loop, but forgot that. So the speed depends, as you can see, on the frame rate. So what is? I don't know. Let's do that. So the speed depends on the frame rate, and we can solve that. But this is a way of dampening down quaternions as well, using spherical interpolation again, and have stopwatch and run that. Frame difference. I know you could do this with timing node, but the timing node. I'm not interested in all these values either, so that's it's like more cleaner a little bit. It's like that. So this is like multiplying a quaternion with this color. You can do it with slurp. Well, given that this color will be between bit 0 and 1. So you can do that. And so this will be a quaternion, and this, oh wait a second, yeah, sorry, this one should be there. And as you can see, it will be very much better now. So now frame rate won't modify the speed of our rotation, and we can fade between the speeds of these rotations very smoothly, even at a little, even at Newton. Oh man, Newton there. So you can fade the rotation, the speed of rotation very smoothly. A little bit, spicing the things up. And maybe we can stop it if you like. Notice if we input into this system or the unit quaternion of this or 1, so we are not rotating at all, it will stop like you would expect. So it won't change the axis for rotation, and only when we change the rotation here, and we will have a short and smooth transition, shortest possible and the smooth transition between the two kind of quaternions. And also I can get, I will try this, I can get the axis of this rotation. Notice I'm not using, for example, axis angle here. I can get the axis of this rotation by using axis angle ket vector, and normalize that. Notice how these values are the same as if I stop here. Notice how these values are the same. So like the axis values coming from the axis angle are the same as the first three components of a quaternion. What I understood from Wikipedia, now there will be like a little math behind it. So if you're familiar with complex numbers, the complex number is consisting of two actual numbers. It's like one is the real number, another one is the complex number, which one unit of that is I is the equal to the square root of -1. Yeah, I think yes. So the square of this imaginary number is equal to -1. So the square root of -1 is I. Yes, not the I. Sorry. Yeah, and we don't know how this number looks like, but we can do magic with that, and physics using that in parts I don't know where, because I didn't do my reading or my learning. Anyway, you can there was a Scottish guy, if I can remember well, maybe I'm completely wrong, but there was a Scottish guy which I don't remember the name of, because again I didn't remember my reading, who came up with an idea of even more complex numbers. So you have not only I, so not only the real number and the imaginary number, but as a complex number with 4 components. So like it's like one real component and then 3 complex components. Irish guy, yes, Hamilton, yes, sorry, Irish, I was so wrong. Yeah, I didn't remember my reading. Hamilton, yes, and he was the one who found out the IJK notation, where I square equals to j square equals to k square equals to I times j times k equals to -1, and in our system, this first 3 number, I don't know the actual math, so I'm afraid I have to direct you to Wikipedia if you are deeply interested inside that. In that topic, but that 3 numbers which I'm pointing at is I, J, and K component of the complex numbers. Yeah, I forgot to mention that when I say a real part and an imaginary part, is a real part plus scalar times this imaginary number. So these three numbers here, what you can see, it will be the axis of our rotation, and these numbers are actually the scalars you have to multiply these imaginary numbers, the I, J, and K numbers. And I don't know how it came up, but this will be that. And the fourth number, this is our real number, and that relates to somehow to the angle, but I'm not really sure. And to be honest with you, in the applied part, you don't really need to be sure about that. I mean, you don't really need to think about it unless you want to do some really, really deep theoretical thing. You have to consider that. But in case of rotating 3D objects around and receiving that from the from any kind of system, what gives it to you is you don't have to. Eval -1. What is that? Andres, I don't know what you mean. EW, yeah, oh yeah, okay. Anyway, -1. Okay, so this will be our axis for rotation, and this will be our angle. Oh yeah, we normalize that. Andres, I'm really curious what you meant with this, because that might give me information I didn't know before. Where was my arrow? Oh, there. So in theory, oh, well, it didn't turn out too well then. It's not the axis what you would think it is. It has other jets. So yeah, don't take that as paper money. I didn't tested this. To be honest, I never expected it. Well, I was kind of expecting this, but not, I was rather wrong. Anyway, so I was wrong. So this axis, what you can see here, is obviously not really representing the actual axis of the rotation around here. And yay, yes, Debian, just joined the best time. Anyway, this is the monkey aside. I was about to do something with that. It is. And yeah, that was a drag. Oh yeah. Use delay from what I type to what you see. Ah yes. I mean, not what I see. Actually, the delay is coming from the stream. Sorry about that. It was related to the other topic. Okay, I kind of forgot that. Sorry about this. So alright, let's see what happens if I switch this, because as you can see, I can actually do that. So this will kind of have the same effect as you could remember before the when we were reproducing the gimbal log with our quaternions. So you could expect we will have yeah, okay, now we have the correct angle. So you have, the correct axis. You just have to do this. We'll flip a couple of times, but actually we do get that. So that's it was connected wrong then. If I wanted to have the correct axis, well, that was my, if that would have been my aim. I mean, in part it was my aim, but anyway. So we have that, and as you can see, it is now kind of rotating in the global scope. Or is it the local scope? It was rotating the global scope before. Okay, first thing is with quaternions you can get very, very, very confused. as I'm a little bit confused now. So if you don't 100% know what you're doing, and obviously you can see here I'm not really 100% sure in what I'm doing. I'm 85%, but as you can see, it can get confusing. Anyway, it's still very worth to try it out if you didn't yet. So alright, let's try this. Let's try this. Oh yeah, look at that. Look at that. That doesn't work. That doesn't work. So it won't work. Yeah, forgot about what I said. It's confusing. Can get confusing. I just don't expect these things. It's like if you want to get the axis of the rotation, then you will get surprising things. So you have to calculate that in your own way. You have to provide that in the construction, so you have to provide that in your system, so you will know what were you doing. Anyway, so that is checked out. Oh yes. Meanwhile, I've got the topic what I wanted to go next, which I forgot previously. So okay, we know now that how we can create. I will just delete. I will just turn it off because it's misleading, and turn this back on to see the line. And so now we've seen that how we can construct like a continuous rotation from any given quaternion, and how to fade between them with you have to fade between them very smoothly, like that. So now I want to get the speed of an input quaternion, and with Euler rotation, that would be pretty simple, right? Yeah, I would just get here. Sorry, so I would just connect this, and it would be just getting the frame difference of that. I hope I'm not telling anybody nothing new. So there we have the difference. We can immediately apply that. Now in case of quaternions, it's not that easy, because actually that. Let me get this back to demonstrate the problem. Holy. Demonstrate this problem. Okay. So quaternions, it's not that simple, because the values are not representing a degree of any sort. Well, the fourth value is kind of representing a degree, but it will be hard to get. It is still just the quarter of the whole information. So what we will do, we will use this system, and let's save it as a subpatch. External Quaternion source. And so I was just reading comments. I'm in the chat. So we have a source of quaternion which we don't really have control over. So we have this, and it will have an output. We have that. What did I forget? I forgot something. Oh, yes. Also, what I also forget is the quaternions. If you feed this one all zeros, it will break. Don't do that. So the default should be on. So the default of such systems, when you construct the rotating system yourself, should always be 001, and you should always avoid these situations, because this can cause you not numbers and all sorts of other spooky things. So let's just initialize that, and there you can have it. So I will delete this, and yeah, it's not needed here anymore. Something about okay. And so we have an external quaternion source which we don't know how it is constructed. However, we want to use its rotation in our similar. Oh, actually, yep, we want to use the speed of rotation in a similar system what you've seen here. So hope we can get that. Now quaternions can be inverted, and I say that I can say if one quaternion and that, I can say that one quaternion multiplied by itself will be, obviously, it will act like a square. If we have an invert of that quaternion, it will act like as the reciproc of that quaternion. So I'm not sure if I'm using the right terms here, but anyway, you can, if you multiply the quaternion with the invert of itself, in the inverse quaternion of itself, then you will get the unit quaternion. It's like the 001, so you will get the no rotation at all, which we can use to our advantage. Is that I hope you are currently suspecting where this is going. So for example, if I connect this and this one, this is like constantly rotating quaternion. This will go, it will be staying the same. You're seeing very jazzy things in the preview, but that's only because of floating or double floating point rounding errors. So mathematically it's the same. I mean, mathematically it will cancel itself. So if I put the frame delay here, I can now have the speed. Can have the speed of this quaternion, and if I put this here, and initialize this, I will have a similar rotating thing in theory. I might mess up the order though. No, actually the order is good. Oh, sorry. So we will have a similar rotation here. So we can use it in our system. This is the external quaternion in our system without, in our animation system, without any kind of difficulties. So let's slurp with that. Or let's just multiply that. With our other angle. And yeah, it is rotated. It is rotated in a way which you don't really presume, because I haven't defined what I want to achieve with this system though. But we can also not only multiply but slurp between the two. Some space here. Have some space here. Can multiply. I mean, we can interpolate between the two. So now we are going in the rotation of this, in theory, while contributing the speed of this rotation to another system what we have, and we can obviously create the same smooth transition what we had here. What we had before. And look, all the transitions will be local. So you have to be very, very, very sure about what you will do. Alright guys, I think we maxed out quaternions, so we can jump over to how we can construct the matrices, or well, the four kind of rotation what we have over here, the matrix transformation. But it's not just rotation, that's any kind of thing, but yeah. And we will use quaternion there as well. Don't worry about that. Another example where quaternions can come from is physics engine. Bullet physics, for example, works with that, and well, it will return the absolute rotation of an object in quaternions, but you will still get the angular speed as Euler angles. This is Euler. Do I pronounce it right? As Euler. Hi Rosie. Nice to see you as well. And yeah. So yes, another source of quaternions usually are devices which have some bit to do with rotations. For example, I think leap motion actually provides you the matrix. But for example, I think Mio, is that pronounced good? You know, that wristband thingy, which can be used for gesture things, which I don't know why it is on the market. Anyway, that's a thing, and it's a rotation. It's absolute rotation. I think it is absolute rotation will be returned back as quaternions. However, I have a friend in Hungary who has this thing, and we wanted to cancel out the accelerometer. We wanted to cancel out the gravity using that quaternion, and that didn't really work out. So anyway. Too much of distraction, and so these devices which that will give you back a quaternion, and now you know how to deal with that. Yes, another thing, another trick I wanted to show you. According to quaternions, so let's get back to our unknown source again. So we don't have control over the creation of that quaternion. So we go back to our source. I won't delete this. I'll delete this though. So again, we have this quaternion again, but let us say that it is rotating. The axis of its rotation is not quite right. It is 30 degrees around. 90 degrees around, or whatever degrees around. It doesn't matter. We will say that is which. So what you can do, I said I won't delete this, but anyway. What you can do in those situations, it usually comes up with skinning, which by the way we will cover next week with Mangouche. He said I should say the VVVV superstar Mangouche. I don't know how true is that, and we will cover the cover skinning next week. So what I'm about to show you now comes up. That problem comes up most of the time in skinning or systems where for example values are, say, the left-handed coordinate systems or right-handed, left-handed coordinate systems, and I might remember wrong again. I haven't done so much reading. Might remember wrong, but VVVV is a right-handed system, and that means that the y is up, the z is forward, and the x is right. Meanwhile, in in other system, meanwhile in other programs, usually other 3D modelers, they use the left-handed system, which is z-axis up, y-axis forward, and x-axis right. And I don't know why, and I'm not sure why these are called. I'm not sure why these are called left and right-handed systems. They have to do something with this kind of hand position. If you can say, well, it's like that. I don't know, but anyway, too much talking, too few actions. So what we can do in a situation where the axis of the rotation is not quite good angled, it's not angled quite well, we can say get this, and guess what? We can rotate the axis around. We can rotate the axis around. Look at that. Large with right hand left. Oh, that's nice. It's the way around. Yeah. I remember that picture. I didn't remember the contents of it. All right, I can't see that. This is what comes up. This is not good. Most math books are right-handed. Okay, so I was wrong again. I'm not the most qualified person to talk about this, to be honest. So guess what? We can rotate the axis of that rotation around. And axis angle set vector. The new axis. This one comes here, and if we say, well, it's not really good in the axis, we just do that, and somehow it is transformed, or axis of rotation into another one, like this is. What I wanted to say. So this is like reversing it, I guess. I'm just rotating it in 180 degrees in one axis. Anyway, you can do that. And just to blow your mind, 50% chance to rewrite, it's okay. Yes. Actually, it's true. It's quite a good chance. So, anyway, so just to blow your mind, we can use the same amount of rotating jazz on just rotating the axis of a rotation. It is ridiculous how complex you can go with these sorts of things, and yeah, way much more complex than what this little node can offer you. Anyway, let's get to these fellas, shall we? These fellas, matrix transformations, because they are the actual jazz. So if anybody wouldn't know, these are well, let's see, maybe we just use this patch. I don't even care anymore, sorry guys. It's obviously we will get a matrix, a 4x4 matrix. This is a transformation, and why it is good, because we can nest in all sorts of, we can multiply together all other transformations. As you can see here, when you are connecting these into each other, you are actually multiplying them together, and you are, well, from mathematical sense, you are multiplying them together. From a human point of view, you are specifying a parent coordinate system in the transforming of these nodes. So the translate coordinate system will be a child coordinate system. We can say that, but I don't know if that is proper or not. Anyway, so what is sure and proper is the compared to the translate node here, which I'm selected here. This rotate node will be our parent coordinate system. As you can see, if I'm translating, it is rotating as well. Well, surprises, and twists in the plot. So why I'm talking about coordinate systems here when these are actually just these are used for transforming objects? Well, these numbers, what you see here, is actually the unit vectors to my new coordinate system. These are unit vectors to a new coordinate system, which is kind of showing the way in my current coordinate system that my destination coordinate system, where that should be, or how that should look like. But so that's like the x vector. Okay, Tabian, I need your help as well here. I wasn't really sure about that in the matrices in row measure or column measure. This is like the unit vectors. This is the x, y, z, and w. X, Y, Z, and W. I presume that this, I think this is like, this is row major, innit? Row major, that's okay, that's cool. So, as you can see, my new coordinate system in the rotation, I'm not moving around yet. So as you can see, you have the new vectors for your new coordinate system's axis. So the x-axis, the y-axis, and the z-axis. Now you have this fourth value here, and that is w with notation, but so 1 x, so 2. Oh, okay. Sorry. So Debian corrected me again that this should be the way around. So x, y, z, and w. Yeah. Oh, yes, indeed. And so what is this fourth axis, you might ask? Is that is preserved for translation, because for translation, okay, first I will show you the problem. So if I will, I'm about to, I will have a little bit simpler case, so you can see what's going on. So that, and let's scale, and that. Okay, sorry. So here, as you can see, I can define rotation and scaling very easily. Scaling, just the x-axis will be like multiplied by 2, and then the y-axis multiplied by 3, the z-axis multiplied by 4. So scaling and rotating is very easy in this case. But how it would be nice to have the translation, because we cannot express translation. Translation would require us to move the origin around, and that would need us all sorts of jazzy notation what we don't want to have. So we just have one nice system which we can store translation as well. And what we need here, and we obviously with the matrix transformations, I cannot move the origin around. So what we're doing is pretty jazzy. We're actually not translating the object. We are let me show you. Yeah. We are actually moving. That is not a good. We're skewing. What is the word for that? Something with. Not that. Anyway, and you know, this sort of transformation where I forgot the word for. I will Google that in a second. Shear. That's the man. Why I forgot words like this? So shearing, and so we actually shear our object in 4D space to translate it around, and then we will project that shearing business back to 3D space. I can show you. So see, okay, this reset everything here. Okay, reset everything here. So as you can see, our translation is stored in this. In the fourth part, in the W here, and we are shearing our object in 4D and then project back to 3D to achieve our translation and stay in a kind of similar system. And this, of course, if you were using VVV for quite some time, or even just new to it, you would see that the projection transformation is kind of the same. It is actually the same system, because you can express not just. You can express also transformation if it keeps up at least with one parallel side. You can achieve that kind of transformation with this system. And the projection transformation, for example, a projection matrix is doing that. It will create a kind of a three-dimensional trapezoid shape to achieve the sense of perspectiveness. So let me show you some tricks, what you can do with it, and how we will translate from rotation to matrices. Just a second. Will. Yeah, I will do. This is not in This is in the VVVV I provided in the, oh, actually it's not in the VVVV I provided because that folder is, I forgot that folder to be in there. Anyway, I will share this patch with you quickly. So I will close this. Define plane transform. From this point, the workshop will go like a little bit random. I will just throw random problems at you according to, well, in connection about transformation, and we will attempt to solve it. Well, I most of the time I solved it, so we will just solve it. And so, for example, first random problem with this is that you have 3 points. You want to find kind of an orientation on the 3 points. So we want to find on the plane these 3 points are the coordinate systems. As a coordinate system, these 3 points constructs. You can treat these 3 points as a triangle, for example. And in MCROPAC, there is a node called, there's a module called find plane transform, which will do this exact job for you. Let us play with that a little bit, shall we? Scaling. So first of all, if we define 3 points, I will show you how that works, how that model works in a second, because that is actually pretty useful to know. It works with cross products and dot. It actually doesn't use dot products anyway, but it uses cross products a lot. And I will explain you what that is in a second. If you don't know, if you know, then comment that, please, or just chat and you write it in the chat so I can decide if I have to explain it or not. So this one over here, you define the top left point, top right point, and bottom right point of just of this square. I will turn on the mouse and the renderer. So this point, I don't, but I'm quite new. You can please continue. Yeah. So now you're not new about this, Andres. You have all the node, all the drone thingies going on, which I cannot grasp. So that's certainly not new, Andres. So this is this node will give you back a transformation. If I wait a second, if I can, I will import Susanne here. Susanne is the Blender monkey. For now, Susanne, hi, and that. Oh. We'll create a separate shader for it. As you can see, it's not transformed yet. So if I connect it here, you can see now Susan's head is kind of taking up the whole cube. So I will just rotate that a little bit. So yeah, the Euler rotations, by the way, is pretty useful for just doing simple coordinate system conversions like what I'm doing right now. Scale. And okay, so now we are inside the box. Back to the topic. So all right, we have this mode here which will which is just create the best fitting and coordinate system what you can get there. As you can see, you can scratch poor Suzanne out very, very badly. You can see it's not really proportional, and we can say that parallel to the horizontal edge, which means the top left and top right, so it will parallel to my first 2 point and the origin to first point. So now our third point is actually playing a role in the orientation of the playing just a little bit of role in the orientation of on the orientation of the plane, and the actual position will be controlled by the top left point. So how this is possible? This is actually built only with VVV tools, and all right, don't listen to all this switching going around here. You only have to concentrate on these two fella, this one and this one. This is actually how you calculate the normal of a triangle, a normal vector of a triangle. So you grab the first two vectors, the first two coordinates of a triangle, then the second two coordinates of the triangle, have the differences of them, normalize it, and cross product it. Now cross product is very, 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 very useful thing. Given two vectors, given two arbitrary vectors, which are not the same and which are not the inverse of each other, so which are not the same and which are not pointing to the opposite direction. So given two arbitrary, completely different vectors, and the cross product will give you a perpendicular vector to both of those vectors. So the product of the cross product will be the normal vector of that triangle formed by that two vectors, and that's why it is possible to calculate the normal vector of a triangle so easily like this. And and of course it's not just the normal vector of the triangle, but the normal vector of the plane which is that triangle is sitting on, as you can see on this example here. So you have your triangle. Let's imagine the edges of the triangle between those points, and given the plane, you have the normal vector here. So we have that. Now we have to construct a coordinate system, though, we need two more vectors. And how will we get that? So what we can do now, we have two vectors which are perpendicular to each other. to get a proportional vector, to get a proportional vector which are perpendicular to both of them, I mean perpendicular to the cross product, or perpendicular to the normal vector, and perpendicular to my original that's perpendicular to the normal vector. This is coming from the normal vector, and to my original vector here, original triangle here. We will just make another cross product between. So the first input will be the first cross product, and the second input will be just the normal vector, the first normal vector, and we will have three vectors then, which are perpendicular to each other. So they can form a proportional coordinate system. Yes, they can form a proportional coordinate system. And you can use that to create a matrix. There's all sorts of switches going on here. Don't give too much attention to it, because that just makes you can select that which vectors it should use for the base coordinate systems. It's like the parallel to horizontal, parallel to the vertical edge. So those switches are taking care of that. However, the more important part is that you don't have to arrange your vectors with zips or cons or Stallone nodes. Anybody use Stallone nodes anymore? To achieve the same matrix representation of your coordinate system, but there is a very, very handy and convenient tool for us, convenient node for us, called parallelepiped. And that is like the parallelogram, the 3D version of a parallelogram. It just means that you construct a coordinate system and you position it somehow. So, but if you feed a cube inside that, under this parallelepiped, as you can see on the screen, it will return that shape. It will return any kind of shape. Actually, I can show you this in a kind of simpler environment. So you can construct your coordinate systems with if you want to do them manually. Most of the time, you don't really. Stallone is totally expanded. I can sense the pun intended in this sentence. Anyway, so parallelepiped. I can actually demonstrate that. There is, for some very weird reason, there is a node which is not the vector version, which is like position x, y, z, x-axis x, y, z, y-axis x, y, z, go on. So yeah, we don't need that, and so this is much more convenient. And where I wanted to go with that is if I connect this one. Actually, let's be coordinate system. Let's just stuck there, and you can see my parent coordinate system will be this find plane transform thingy of the parallelepiped. So we will see what's going on, and we don't have to disconnect anything. So defaults are already there. So one that's here. So if I change any of this, as you can see, I'm changing the y-axis, and then this I can change the z-axis like that, and then completely distort the cube like this, and this will result in all the I'm not sure though that all the sides are parallel. Yeah, all the opposite sides are parallel to each other, but this will obviously be completely distorted thing, and that is also demonstrates what you can do with the 3x3 matrix transform. So you can't do all that trapezoid jazz and the perspective and translation. You can only achieve this kind of parallelepiped business. What you can see here. So let's put aside. Oh yeah, Debian, future requests. Please do not tag a patch as changed when the only thing what I'm doing is scrolling. That sometimes it's annoying, but it's not annoying enough to post that actual thing in the forum. So yeah, feature request and feature request. Yes. Yeah, so that was a random problem. So how do I find a coordinate system which is kind of lying? How do I find a transformation which is kind of lying on the plane? So you have find plane transform here, which is part of MPCR pack. So set aside, this is a bold patch. We have another problem with this, with transforms. I want to show why I have. Let's stick with this then. So what if, okay, David, I only have a vector. I don't have a word triangle. I want to find the transformation just based on that vector. So obviously what you can do is use lookat, and that will most of the time do your business. But look at what happens here. There is an up vector which will actually define the role of your looking business. I will show that to you, and I will make Susan look at things. So, oh yes, sorry. So as you can see, I have to add this to that. Actually, what I can do is use transform multiple. This little fella is also very, very useful, super useful stuff. If you don't want to connect all the time the the highest level transform, if we can say that. If you don't want to comment all the time, we will you can use this node here, which is kind of does the same as just connecting it to the top level, and that's kind of, it does the same. So boom, boom, and this is useful because there are systems which will not provide you this transform in, and then you have to use it. And this is also useful just because of convenience. You can set up a set of these transforms to sit in the same system, to sit in a separated system, so you can treat them individually. Anyway, the rule of this is that the rightmost transforms is the topmost transforms here. So the bottom transform is on the left, and the top transform is on the right. So that's the rule of that. And back to our original problem. I have only a direction, and I want to construct a vector. How do I do that? And I have, for example, this direction, and I will create an arrow, this one, and oh man, 6, I don't know, 12, that one, and this arrow will be transformed this so we can see it, and multiply by 3. Oh, okay, so that's actually pointing down. Yep, it's pointing down. Oh, okay, it's pointing down because my z coordinates, or I use the z vector for the normal vector to the plane, which is coming from the affine plane transform. Currently, this is the behavior. The reason why I've done this is because I've developed this affine plane transform to use with the touch screens most of the time. You know, those kind of camera detected touch screens like Kinect or with leap motion. We had a conversation on Facebook, I think, with Gui, that actually generated this node. I mean, he requested for something like a homography for 3D, and then I've done this. So anyway, yes, our arrow now currently points at that direction, and if I save it again, and can make the monkey obviously point. So where's my arrow? Oh, there. Okay. So it doesn't actually line up because I rotated the monkey. Oh my god. Yeah, you have to be careful about this as well. So this one again, we use. Now I want only this rotation. Look at what I do. I want only this one, but I don't want the lookat to influence my rotation, so I will use the transform multiplication again. Yep, the rotate comes. I mean, the rotate is on the lookat, and Oh, it's much more. Nah, it's not consistent at all. I can't show a thing. Alright, now we start a completely new patch. Sorry about that. For example, this one, which we're loading the patches into. So that render. Let's have an axis angle. Axis and grid. Group. That camera. Space mouse. That. This and that. That. And Havor Susanna. Scene file. Workshops and look at problem. Jesus, I'm just still demonstrating the problem. I haven't come to the solution yet. And group again. This is on the high, and this and that, and standard. Well, I can understand now why newcomers to vvvv is not really keen on the rendering system or rendering pipeline. So we have a season, amazing. Aspect ratio, just we don't get this even out of this. And then we have on arrow this direction, and I also figured out what was the problem originally. Is that, sorry, I haven't used lookat for a while. Is that we have to inverse that to apply it on objects, because this exact node was designed for camera matrices. So that's why we were not seeing anything. The value multiplied by 2. It's my arrow. Yeah. My Susanna is not looking at the right direction, looking at the opposite. And well, yeah, let's make the lights a little bit better, like that. And oops. And let us see what we have here. No, very nice. Okay, normalize this. Very nice. And oh yeah, just I was using so much time that I haven't explained what normalize does. It just makes your vector, makes your length of your vector to 1. So it actually just divides your vector with the length of your vector. Just in case anybody didn't know that. And look at that. And we can see that this lookup node is actually doing a pretty damn good job. But what the problem is with that is, look at what happens if I want to make it. Look at the y-axis. Whoop, whoop, oh, whoa! That is some. All right, so there's some jazzy things going on. Now what's happening? Why is that happening? Notice this up vector. So this one is actually helping the lookup to construct a matrix. If this vector is the same as this one, and one of the cross products which is in the lookup somewhere, or one of the cross products which is in the lookup somewhere, something is giving back an error or an infinite or something undefined, and that's why we will have this ridiculous phenomena what is happening here. As long as it's not the same, it will give us the right vector. So we can make that many VJs use this lookup tree. Yeah, indeed. And okay, was it a pun? Was that a pun? Or was the serious? We will so either way we will provide an up vector which is kind of perpendicular. Sure. I don't know which sure. I'm confused, Debian. I'm confused. So this one, we have to provide a vector which is not the same, or at least not pointing to the same direction of this. Oh, you mean this one, Debian? You mean that? Okay, so that was actually not a pun, and actually a lot of VJs are using this. I can understand that. I'm not really good with at some yes, okay. So we have to provide a vector which is not this, and most of the time it should be kind of I wanted to say it too quickly. Yeah, and most of the time it should be like the perpendicular or just an axis pointing somewhere. Anyway, solution to that problem is as another node. Did I create that node? Oh yeah. Okay, I just overwrote that. Anyway, there's another node called look at simple in MCR opaque. I just created this today, and this is basically the same, but it will find you a vector. But this, as you will be able to see shortly, this will produce you other jazz. And direction, no smoothing, depth. So as you can see, now we have or vector, we don't have to define an up vector, and this won't make your model. It's very this won't make your model disassembled or scrambled like that before. So it won't make any kind of errors. But see what it does. Whoop. It's not good. So if you are using this for animation, you might consider it. You might consider this. I mean, you might consider this behavior, not this node, because most of the time, as I said, look at will be good for you. However, sorry, it was a mistake. However, let us see, you want Suzanne, you want to form a sphere of Suzanne's, then it might be a node for you. So we have the spherical spread. And let's see, we want 16 Suzanne's. That we normalize that. Connect this one here. We have all sorts of Suzanne's going on. Translated. Well, what was that? Translate now. As you can see, there is some kind of consistency, I guess. But anyway, it will give you kind of an evenly distributed rotation around the sphere. And if I do the same and look at with the proper lookup, with the lookup vector of the y-axis, see what happens. So this is actually nicer, but it will align your objects on that axis. So if I say like vector should be this one, then I'm in trouble now. Is there any way to avoid the lookup VJ glitch? Yes, there is a way, actually. If you don't want to use this thingy, then what you could do is okay, there are several ways. First, use dot product to determine like this. So to determine the kind of similarity between the up vector and the current vector, we can use the dot product, and if the absolute value of this equals to 1, with an epsilon to leave space. Yes, indeed. Actually, everything adopted VVV look. VVV started to be flat before it was cool. So we can tell. We can say that to switch to certain vectors, so this is our first option. So if it's not equal, then just be there and switch to a vector which is like this, and then slide it's like this. This is like a very little very little difference or very little movement in on one axis. So we can avoid the glitch like that. And but not this. Oh, actually, yeah, we have to normalize this because we're dealing with directions, and most of the time you have to normalize things. So as you can see, you won't end up with that problem, but you still end up with this kind of behavior here, which is like moving around. So the other option, what you could do is I'm doing the same here, so I will just copy that, is that have all the vectors here, all the axis vectors here, and these will serve my my up vector. Do the dot product. Do the dot product to all of these. So I will just remove this then. That was one method. So do the dot product because this will be a little bit better. Do the dot product to all of those. And sign. We only need the absolute part of the dot product because we want to check for opposite axis. Oh yeah, just to show you. So this is messed up, and the other direction is messed up too. So yeah, should be good. By the way, survey, are you still hear me and see me in good quality? If you can, just say yes, and I will be resting. I will rest in the knowledge of this stream is not going apart. So anyway, we have the absolute part here, and we will do a little normalization and that jazz. So we want to have the vectors. We want to weight the vector. Okay, yes, that's cool. Very good. Want to have these vectors. Want to select a weight between these vectors, the weight between these vectors based on how much close they are to the zero, how much close their dot product is to my input vector to 0. And this is a way how to do it. It's like subtracting the dot product, absolute part of dot product from 1. Do normalization on the data, using a power for little smoothing out there, or if the animation requires. And then finally we have the vector. David Maruszczak. Oh, a new Hungarian fella on the VVVV scene. That's a good news. And we will just connect this to the UNCUT up vector. And what we will see some the similar kind of jazz what we had with the UNCUT simple node. But it will never, I will guarantee you, it will never ever do that glitch thingy. However, if we connect the to this, and then that, and then we don't have those very nice lined up monkeys now. So it's kind of like a debate. You want to have the do you want to have the total freedom of those directions, or if you know that your vectors probably won't end up looking at upwards, then you can use this method, and you are lazy to calculate your actual, because this is quite a cheap way of, which is quite a lazy way of calculating an always perpendicular method. So yeah, oh, okay, one last thing I want to show you guys is how to interpolate between transforms, because that's not, I've seen a couple of people asking that, and or doing something weird. So actually we will do this. We'll do this here. I don't want to open or have a new patch about it. Oh man. So we want this monkey. Okay, why does we do that? I don't feel like I'm in total control of this situation right now. Anyway, that was weird. And so we want that monkey to form into, we want that spherical spread of monkeys to form into one single monkey. But let's assume that we don't have the control over the transforms. So again, let's assume that we have a source of transforms. We don't know how it was constructed, and but we want to blend between them. And one way to do that is, I know some people will scream in agony, but it is with decompose and with, again, quaternions. And I will fade between this one and one. Sorry. One with like that. Maybe like this. And I've seen, actually, when I was young and didn't know about things, I didn't know about how things work, I was doing this, and this is very, very wrong. But you will see. And you will see why it is very wrong. So this is just linear interpolating between the values. So that's not good at all. And you immediately see why it is a very bad idea. So never ever do that. Indeed, so this is forbidden. What you should really do is decompose, transform, We're a little bit looking back at rotations now. We can linearly interpolate between the position though. And the scale. But we have to spherically interpolate between the rotations. Like that. And obviously all of these should receive the same driving value. And then construct on transform. Translate first, then scale. It might be a little bit different, but to be honest, it doesn't really matter. What matters is the translation should be the top one, but scale and rotate can be swapped. And rotate with Quaternion. And as a result, you have a very nice monkey. You have a very nice monkey like this. Can break out. So yeah. Clap, clap, clap. Applaud. Anyway, this, I think this was enough for today. I don't have anything better to show you around the rotations for today. I could show you about shader, how to do this in shaders, but I'm not that prepared with not that prepared to do that, and that would be a huge amount of times. So I hope you enjoyed it, folks, and should be module if it's not already. Wait a second, do I have it in module? Input morph transform. Yes, it is. It is a module, but it is the bad kind of module. So don't ever use that. Actually, is that? Yes, that is mine. Don't ever use that. That is the old one. No, never use that. I will use that. Yeah. So, oh yeah, greetings from Budapest as well. This concludes my workshop. I will update that input morph transform to this one, and with that in MCRO pack or an atom pack, I don't know. To be honest, the pushing business with atom pack, another repository, it's just I'm a lazy person, too lazy to do that. And next week. We will do. Thanks, guys. Thanks very much. And next week we will do, based on this workshop, based on much knowledge from this workshop, will be transferred to the next week one, which will be about skinning. And just for a little bit of teaser trailer, we will skin a character with Kinect, with proper rotations and all sorts of jazz. So that's a thing. I will put the patches up. What? To be honest, I haven't kept any kind of consistency between the patches. So the remaining part of them, what was the result of this mess, what I've done here, will be shared on Google Drive in the folder. And I plan to do this weekly, obviously very much more prepared. And in December we will have the first guest tutors as well. In December, yes, I've said December. So more information on that later. Well, when it comes, it will be awesome. And yeah, I think that's it, guys. See you next week, and I will just fade. Could do all the episodes somewhere. Oh yes, I had it in mind. Who should I ask for Vodio? Vodio. Who did that? No, thank you. That's really appreciating. So, Tembion, you can do that. If you can do a workshop, then I have a free space in November. Or if you want to do that later, we could speak about it. Yeah, nice. Okay, then we will have a Vodio workshop at some point. And I have currently 3, or now 2, rather later. Okay, then I will have 3. I will keep 3 more workshops in November. There will be there are planned to have 4 workshops in December, and about graphical stuff, and we will graphics and shading. I also suggest we can do the Vodio in the beginning of January, maybe, if that's good for you, Tabden. Well, we will talk about this later. Anyway, yeah, more questions from on IRC or I don't know. We can start a hangout, a private kind of hangout. Yeah, anyone can join. I will share the link in the video description. I will try to create a hangout actually. So you have a little community conversation over there. The Vodio before Christmas would be great. All right, okay, we consider that, but guys, Christmas is like 2 months, not that long, and this is 1 workshop per 1 week, so that's currently the thing what I can do. Okay, it's fun. Ending soon. This is like the end. So again, guys, thank you very much. Return of audio, and I'm not good with endings. I will just turn it off. Bye.